All right, hello everyone. Thank you for attending. So I'm Edwin Alexani. I will be your host for tonight. And so I'll be talking about the formation of planet in systems. So this is with the UCLA Planetarium. So let's get started. Why do we care? So up until today, there have been up to 4,551 exoplanets that have been found. And more than that amount is actually waiting to be confirmed. A lot of them have been found, more than half, actually have been found with the Kepler telescope. So that telescope has been very useful to find planets. Now, if we find this many planets, then that means there are more worlds out there, and we have just begun. The first exoplanet was found in 1995, so it's barely been about 25, 26 years that we are finding exoplanets around other stars. And so as we begin to find more and more planets around other stars, we might think, well, how common are planetary system like ours? Are we going to find a lot of terrestrial planets and gas giants on the outside, or are the configurations a little different? And can we account for those different configurations that we see? There have been Jupiter-sized planets that have been observed to be much closer to their parent star than our own Mercury is, for example. So, can we account for these differences? And finally, how common are planets like Earth? If we're going to be talking about planets, we live on one. And so it would be good to know how the Earth came about. So before we know how planets form, we need to talk about how stars form. And so this is part of the nebular hypothesis. The first part is you need a cloud to collapse. So throughout the Milky Way and throughout different galaxies, there are molecular clouds and there are also dust clouds. And we are more interested in the dust clouds, and we need those to collapse. Um, and they're going to collapse under some sort of outside pressure. Maybe there was a supernova nearby that started compressing the cloud, or the cloud traveled through a spiral arm and that is causing it to collapse. Or even there is some loss of pressure within the cloud. Whatever the case, there is some mechanism that is causing it to collapse. And so most stars will actually form in groups. So stars do not form alone. Even the sun actually formed in a group, and that group eventually dispersed over time. There is even a possible solar sibling, HD 162826, but it's not confirmed yet. But people are just trying to figure out if there are other solar siblings, and if so, those could be the best candidates to look for planets like Earth. Um, Regardless, the chemical composition of the nebula will affect whether or not you can get planets like Earth or planets at all. And so that composition will be affected by where you are in the galaxy and when you are in the galaxy. As it turns out, over time, when stars die, explode, and release the materials they have created in their cores through fusion, those are the heavier elements like carbon, oxygen, silicon. Those are what can form the rocky cores of planets like ours, and even potentially the rocky cores of planets, say, like Jupiter, that would need an initial starting point. Um, and so, anyways, as that star forming cloud is collapsing, you have a protostar that starts to form in the middle. So you can imagine a big bubble in the middle, and then there's still the rest of the collapsing cloud around it. So over here, if you see the antennae galaxies in the corner, what I really want you to notice is those red regions that almost look like blisters. And so those regions are in undergoing what is called starburst. Because these two galaxies are colliding, you have a lot of compression of gas. This here is in our own galaxy, the pillars of creation. So all of these structures, inside of them, there are stars forming. And so we usually observe them in the infrared because that is the wavelength at which dust is heated. Ironically, humans also emit infrared wavelength. That's your body heat, right? Those thermal cameras, it's infrared. Um, Now, a question for you is why doesn't the entire cloud form a star? So I'll get to that in a minute. But before I do that, here is the Orion Nebula. And so inside of this, if you see this little square, we have it zoomed in at the bottom, you can see some light escaping. And so that is actually the protostar in the middle of this disk, and you can see there is a lot of dust around it, and so that dust would be that initial collapsed cloud. And here are more of what we call proplids. So it's when you have little bubbles of gas and dust that begin to collapse. So that's what they're called. Now, again, back on the question of why doesn't just the whole cloud collapse to form a star? Well, what happens instead is you get a protoplanetary disk around the star. And this has to do with the conservation of angular momentum. Now, those sound like big fancy words, but they don't need to be. Angular is simply the distance of some rotation. So, for example, if you have an ice skater here, her arms are rotating away, right? That's the angular component. Notice when she pulls her arms in, she spins a lot faster, and when she lets go, she slows down again. So I'll replay that for you one more time. So right there, that is the conservation of angular momentum. The closer it is to the center, the faster that, in this case, person will spin. And momentum is simply velocity or speed times the mass of that object. So if you let the whole cloud collapse into the star, that star would spin too fast, and in fact, it would rip itself apart. So you couldn't just collapse the whole cloud to get a star from it. Now, if there's just, enough to make the star, sure, but that's not usually how it happens, because for a cloud to collapse, you need it to be much, much more massive than what you're going to end up with your end product. So, you could have 10 times more mass than you need in order to form something like the sun. Now, what happens with the rest of the collapsing cloud is those little dust particles, they keep colliding into each other, and they slow each other down, and eventually they cancel the up and down motion of each other because they kept getting hit. And so you settle into a disk over time. And over here you can see this is a real picture. It's in the infrared. So we have the star HL Tauri in the middle. It's a protostar. It is still forming. And around it, you can see gaps and rings. So in the gap regions, that is where you are going to have the planets forming. And you can think of it as a snowball, for example, right? So it's kind of cleaning a path around there. And then in those rings, there is still some remaining material that can either be taken by planets or something else will happen to it, which I will get to. Now, what are the effects of distance and time or timing on the planet formation? So think about that for a minute. Now, before I get into that, let's take a closer look at these protoplanetary disks. So there are many of them that have been taken, and a lot of the credit goes to ALMA. So it is the Atacama Large Millimeter or Submillimeter Array. It is in Chile, and Atacama is just the name of the desert that it is in. And so, for example, if you look over here again, that's HL Tauri that we looked at. Over here, you have another one which is a lot more circular. So maybe HL Tauri is at a little bit of an angle with respect to us, but this one seems to be face on looking at us. And again, you can see in this region there is a gap, so there's probably a planet in there. Same idea over here. There are also some ring features, so the planet will be located here, for example. Now, this was a simulation on the left. So at the top, the spiral one, that was a simulation. And on the right, you can actually see a real example of such a simulation, except this is an actual picture on the right. And again, there are many more of these objects. So this is confirming the part of the nebular hypothesis that you do end up with a disk that will help form planets around that disk. So part 3 of the nebular hypothesis would be planet formation. So what does a distance have to do with the planet formation? It turns out at a different distance from the star, you're going to get different temperatures, right? If you're closer to the star, then you're going to have a lot warmer conditions. And the farther away you go, the colder it gets. Well, it turns out that is going to affect what can and cannot form in that region. So within the frost line, closer to the star, that's where you will see dense elements like metals, rocks, and those are the first ones that will be able to solidify under such high temperatures. If you want, think about trying to melt iron on Earth. You need very high temperatures to melt iron, which means it can withstand those really high temperatures closer to the star, and that's the first thing that will be able to solidify. That is how you get terrestrial planets. When you go beyond the frost line, that is where you get ice formation. You can get water ice, you can get ammonia ice, different types of ices, um, which are usually what we would find on Earth as a liquid or as a gas. So, nitrogen, for example, is a gas on Earth, but farther out, those could actually be in the form of ice. Now, um, how do you get from a cloud to a planet? Well, first you have those little dust particles, then they stick to each other, they form little rocks. Then those rocks begin to stick to each other, you get asteroids, the process repeats, and you get planetesimals. At that stage, things start to get a little violent, and eventually, if any of the planetesimals survive, then you can have an actual planet. And what do I mean by things can get a little violent? Well, there is this great animation right over here. So this is another simulation which will show what happens to the cloud as it collapses and starts forming planets. So over here you see those are planetesimals. Right there, one of them got absorbed back into the star. This one collided right there. So if you missed that, I will go back in time, which we cannot really do, but with videos we can. Notice right here that in the middle, and then more things are going to happen as time goes on, so I'll slow it down again over here. So notice those two planets near the bottom have a very close encounter. One of them is getting pushed out of the system and is probably going to get ejected completely, while the other one gets pushed towards yet another planet. So that is going to kick one of the planets into the star, and then you have two more planets that are colliding. So even though you can start with many small planetesimals forming, they have to survive because they have gravitational attractions towards each other and they will be affecting where one planet goes, where one can stay. And so, again, many of them can form, but it's a matter of survival. It's very, very chaotic when you have all of these planets going around. And again, the note about thinking of the different states of matter on Earth, that was again back to the frost lines and where the different elements can form. So far, we have talked about how you can have a cloud of gas and dust that needs to collapse. As that cloud collapses, you get a protostar forming in the middle. And around it, you get a disk of gas and dust. And that disk has to form because of the angular momentum problem. For example, the sun has 99% of the mass of the solar system, but it only has a fraction of the angular momentum, while Jupiter has about 60% of the angular momentum. Why? Because Jupiter orbits farther out from the sun, and so it is rotating. And it is that rotation from such a removed distance from the sun that gives it such a big amount of angular momentum. Now, gas giants must form before the protostar enters the T-Tauri stage and subsequently ignites, meaning before fusion starts inside the star. As soon as that happens, it will blow away the remaining material. So before we get to that part, here you can take a look at the different elements and their abundances as you go away from the sun. So on the right, you can see this diagram. Mercury formed very close to the sun, so it formed at a place where the temperature was about 1,600 degrees Kelvin, and it was very close, within 0.1 or within 1 astronomical unit. 1 astronomical unit means one distance from the Earth to the Sun. So those are astronomical units. And then Venus formed at about 1,000 degrees Kelvin. The Earth around 600 degrees Kelvin, which is still very hot. Do consider that 273 degrees Kelvin, that would be the 0 degree Celsius. And so if you are at 600, that's 300 degrees Celsius. That is very hot. Then you have Mars, forming a little farther out. And now notice all of the ices, including water ice, actually form far beyond where the Earth would have been. So how did the Earth get water? We will get to that soon. But before we do, we can also take a look over here at the different abundances and notice that the planetary trend is followed pretty closely by what we would expect to see. From the distance to the sun to what we expect to see to solidify at those distances. Now, here's a timeline of what can form at different times during the collapse of the cloud. So initially you have the cloud collapsing, and it takes about 1,000,000 years for the sun to form before it enters the T-Tauri phase. And as that is happening, about 500,000 years into this stage, you have rocky grains forming in the inner solar system. So that is us. We're part of the inner solar system. Now, at the same time, the gas giants already begin to form because you have the icy grains which form sooner than the rocky grains. They're able to solidify sooner because they're farther out, it's colder, so those solids can form faster. This gives the gas giants a head start, which also does contribute to why they are able to accrete so much more mass. Now, as you continue, do you see this dashed line over here? That's pretty much a deadline for the gas giants. As soon as the star ignites, meaning as soon as nuclear fusion begins at the core of the star, what happens is there's radiation from the surface of the star that will start kind of just blowing away the rest of the nebular gas around it. Now, this doesn't affect the dust as much as it affects the gas. The gas particles are a lot lighter and a lot easier to kick away, but the dust particles are a bit heavier. So this mainly will affect the growth of the gas giants. Now, let's recap what is explained by the nebular hypothesis. So, because we have this disk of planetary formation, this accounts for planets orbiting the star in nearly circular orbits. For planets orbiting the star in the same direction, all the planets in our solar system go around the sun in the same direction, counterclockwise. Then planets can also orbit the star in the same plane. So it's not like you have one planet orbiting like this, one of them being like this, the other one being like this. They're all roughly around the same plane. And they are distributed in the system along those primordial abundances. What do I mean by that? You see the terrestrial planets on the inside and then the gas planets on the outside, which would go along what would be predicted by the model of the denser elements on the inside and the lighter elements on the outside. Now, it also explains why there are small bodies left over, like asteroids, comets, dwarf planets, and why planets rotate in the same direction. There are some catastrophic exceptions, but that is just a artifact of what can happen in these systems. Now, the solar system is made of the inner solar system. So here's Mercury at the top, very small, Venus, the Earth, that's the moon. Here is Mars. This is Jupiter, which is now part of the outer solar system, and Saturn. Now, Jupiter and Saturn are considered to be the gas giants, while Uranus and Neptune are considered to be the ice giants. And these, I made sure that they would be shown to scale. So in real life, this is actually how the planets compare. So if you look at the Earth, it is about the size of this storm on Jupiter, the famous red giant spot. So why is it that Uranus and Neptune are so much smaller than Jupiter and Saturn? It seems like they should have been gas giants too. I'll get into that in a moment. But before I do, we have to start with the inner solar system. That's where we are. So electrostatic forces, which is the same force that would happen when you rub a balloon on your head, for example, and then it sticks to a wall or it just sticks to your clothes. But imagine that with dust now, and actually you can even imagine a dusty computer and how the dust kind of just sticks to the screen. So a same type of interaction is what helps the dust stick to each other at the beginning. And again, we went through the process that, the dust eventually turns into rocks, into asteroids, and into planetesimals. Now, Earlier, when you saw that animation, there are catastrophic collisions and interactions. For instance, Mercury has a massive iron core. When we compare all the terrestrial planets with each other, Mercury has a disproportionately bigger iron core. And so we wonder, well, what could have happened that could have caused this? One possible reason would be an impact, as you can see at the bottom, that would have completely stripped away Mercury of most of its outer layer, but then it would have kept the core of the primordial Mercury and the other planet that hit it. And now we have modern day Mercury. So it could be that Mercury used to be a lot bigger, but then it lost a lot of matter because of this collision. There's also Venus. It actually spins backwards, and it spins very slowly backwards. So a day on Venus lasts longer than a year on Venus. And so what could have happened is as Venus is spinning like this, maybe some object hits it from the side and starts pushing it the other way. So it must have been a massive collision that would have changed the way it spins. There's also the Earth's tilted axis, which causes the seasons. Without this tilted axis, we would not have seasons. But why is it so tilted? And this could be related to the fact that we have a moon. The Earth, when it initially formed, it was not massive enough to create a mini solar system around itself from which the moon could form. So what has been hypothesized is that there has been a moon-forming impact from a Mars-sized object that could hit the Earth, and then from materials spewed out from both the Earth and the impacting planet, that is how you would get the moon. Otherwise, the moon is far too large for the Earth to have just been able to form it from a ring of gas and dust around itself. There's also Mars's moons, which are either thought to have been captured from the nearby asteroid belt or to have been caused from an impact. But regardless, those moons, again, could not have just formed because of Mars's size. Mars would be too small to create moons on its own the way that gas giants would. Um, and so here now we can take a better look at the cores that I was talking about earlier. So notice Earth has a lot of mantle to go around and then a decent sized core. The same goes for Venus, Mars, and even the moon. But notice Mercury, there's this tiny sliver of a mantle and this massive core. So that is something that stands out. And there's probably a catastrophic reason for this, probably that impact that I was mentioning earlier. And now, this is a perfect segue to go into the gas giants. You can notice the composition of the gas planets. So all of them do have a silicate core. Now, silicate just means rock. So silica comes from silicon and oxygen. And so those two make a molecule together called silica, and that's what makes up rocks. And so that is the basis of what can then form around those gas giants. That's how you get the ice on top of it, and then you get a lot of hydrogen and some helium too. So the outer solar system, again, has a head start because the ices can form sooner. And so as those ices form, then you can get a lot of gas being swept around. And in fact, Jupiter and Saturn began collecting gas first. That's because they were closer in, and so there is a giveaway. You do get more matter sooner as you go farther out, but then there's at some point you also have less and less gas and dust to go around. So Jupiter and Saturn were just in that spot where you are beyond the frost line, but you also have a lot more material than farther out. Uranus and Neptune eventually started to collect gas later. Now, the gas giants, they are massive enough to start pulling in material around themselves, and it starts to look like a mini solar system. In fact, there are many moons that are around Jupiter, the four Galilean moons. Those are big. One of them is even bigger than Mercury. So if you plucked Ganymede, which is the moon bigger than Mercury, and put it around the sun, it could be considered a planet just based off its size. Now, there is a moment where all of this stops. Remember the timeline earlier. As soon as the sun ignites, the solar wind will blow away all these gases. Now, you can see this represented over here. There's a bow shock around a young star. and HST means Hubble Space Telescope. So that's the telescope that took a picture of it. So as soon as the fusion starts in the core of a star, it will then blow away the gases and you get kind of a bubble. And that will stop the growth of any of the gas giants. So this is why Uranus and Neptune are a lot smaller. Now, on the topic of Uranus and Neptune, they actually swapped places. So it turns out Neptune formed closer in, and Neptune is actually heavier than Uranus. But then there were some instabilities in the orbits, and you can see those kind of going up and down. And what that means is it's the instability that's causing them to shift back and forth. Eventually, they settled into the present day orbits that we see. And these models over here, those are called the Nice models. And so those are just some representations of what could have happened. Now, as this happens, this is a disk of material that is left over from the formation of planets. As the gas giants are moving around and shifting and migrating, this is starting to kick all of these asteroids all over the place, which is bad and also good, depending on what you're thinking about. It is good because it brings in water to the inner regions. And this period is called late heavy bombardment. And then the leftovers is just what I'll discuss after. But so the period of all the asteroids coming in, that is the late heavy bombardment. It is triggered possibly by the migration of those gas giants. Some of the material just gets kicked out into the Oort cloud. Now, the Oort cloud, you'll notice over here in this picture, it is kind of the last edge of the solar system between what we consider to be the interstellar medium, which is the space between stars, and our solar system. Then these icy comets can also either go out or they can go in towards Earth, for example. And so that is how Earth got water, because the water could not have just formed ice. It was too hot near the sun at that time. But those comets are what brought the water to Earth. Now, most of the craters we see on bodies around the solar system are from this time. So this first moon over here, this is Callisto. It's Jupiter's moon. It is heavily cratered, and it is because of this time period. This is Miranda, Uranus's moon, and it was almost completely shattered by an impact. It barely survived. Um, Now, there are leftovers from this violent period of formation, and those leftovers are the asteroids that we see in the asteroid belt, which is between Mars and Jupiter, um, in the Kuiper belt, which is beyond Neptune, and in the Oort cloud, which is where you find comets. There are also dwarf planets left over. So Eris is the biggest dwarf planet. This is Ceres. It is actually found in the asteroid belt. And this is Charon, which is Pluto's moon. And here's Pluto with this little icy heart. And these are the latest pictures that were taken recently. So, enough about the planets in our solar system. What about exoplanets? After all, if we're interested in learning about how planets form, we can't look at our solar system because it's already formed. We need to look outside to see what can happen and what different configurations we have. How do you go about finding exoplanets? So there are four main methods. There are different methods, but those are the four that yield the most results. So the first one is the Doppler effect or radial velocity. This is the one at the bottom. So imagine you have a star and you need a planet that is pretty heavy or pretty close to its star that we notice a wobble in the star's light. So the same Doppler effect that affects the sound of a car, for example, when it passes by, the car horn, I should say, right? The same effect actually happens with light too. And so there's a blue shift when the object is moving towards you. That would be kind of like when the car is moving towards you. And then there's a red shift if the star is moving away from you or the car is moving away from you. And so if we notice a periodic blue shift and red shift, then that periodic change is what could hint that there's a planet around that star, right? If it's completely irregular, then it's something else. But if it's very regular, then that means there's most likely a planet. that also means you need to take many observations, right? You can't just see it once and say, oh, that's a planet. You need to see it a few times. There's also the eclipse or transit method. So this is in the same spirit that you need to have a planet, um, in this case, crossing in front of its star. And what we would notice is not a periodic red shift or blue shift. We would notice a periodic dimming in the light and then going back to normal and then dimming again, going back to normal. And so, again, you have to take many observations. What if there's just a little speck of dust going in front of your telescope? That could dim the light of the star. You can't confirm a planet right away. You need many takes. There's also gravitational microlensing, which is shown at the top. So basically, it turns out if an object is heavy enough, it can actually bend the light around it. So if you have one star over here and then another star in front of it, as this star passes, if there's a planet around it, then that planet will also have its lensing effect around the planet too. So you notice this little irregularity over here, in the brightness that would increase, and that would be hinting at the presence of a planet. And then there's just straight up taking a picture of the planet, direct imaging. Now that is obviously a lot more difficult, but as our equipments get more sophisticated, we are able to do this more and more. But there's a selection effect in these detections. A lot of these planets that we find initially were hot Jupiters. And so hot Jupiters are Jupiters, right? Jupiter-sized planets, very massive planets. So they're big, they're just screaming, hey, I'm over here, right? You are easily going to detect those. Whereas planets like Earth are a little more difficult to detect. Now, hot Jupiters are one aspect of exoplanets that we actually cannot explain with the nebular hypothesis, right? Hot Jupiters are found orbiting their host star much closer than Mercury is. In fact, many hot Jupiters orbit the star within a period of days or weeks. So that is very close to the star, and that is not explained by the nebular hypothesis. Does this mean it is wrong? No, it could mean that it is incomplete. Perhaps that Jupiter decided to migrate over time and settle into a much closer configuration, or maybe a nearby star sent the Jupiter much closer to its star. Whatever the case is, there is some migration that is happening. And if there is that migration, then what does that mean for any planets that used to be in there? Are they going to get kicked out? Possibly. So that is one thing with hot Jupiters. Now, there's also super Earths that have been found. So they're rocky terrestrial planets that are many times the mass of the Earth. And in fact, there was a presentation earlier on super Earths with the UCLA Planetarium, so you can check it out on YouTube if you want to learn more about super Earths. And there's also another peculiar exoplanet system that has been found. It's been a few years now. It's TRAPPIST-1. It's a personal favorite of mine. So it turns out, if you look over here at the bottom, you see there are 7 planets. Now, the planets that we see over here are to scale. So if you took, let's say, TRAPPIST-1b, the one that kind of looks like lava, and put it next to Earth, that's how big it would look. But it turns out all of these planets orbit within just this tiny distance of their stars. So all of these orbits have been enlarged 25 times. So imagine you have 7 roughly Earth-sized planets that manage to stay in a stable configuration around each other. So how does that happen? There is some resonance, which means that the planets pretty much kind of for example, when you have a swing and you push the person on the swing at the right time, they can go higher and higher. So there is some mechanism like that that is keeping the planets stable. Now, how detectable are we? Well, these are the planets that we have been able to find. So if this is a planet that has the mass of the Earth, right, we would be on this line. And for the orbital period, notice this scale is logarithmic, meaning it gets 10 times bigger each time. So if this is 100, this over here is 200, that over here is 300, and the rotation of, or the revolution of the Earth around the sun is about 400 days, right? 365. So we would be roughly here. Well, that's it. We've only found about one, right? So it's not too many that we have detected that are exactly like us. And again, notice most of the planets are found at much closer orbital periods, and they tend to be heavier too. And that is again the selection effect. It's not that other planets like Earth aren't out there, they're more difficult to find. And the farther that planet is from its star, the longer it's going to take for us to be able to confirm, right? If it takes 1 year for the planet to go around and we want to take many measurements, that's many years of observation. So, does anyone have any questions about anything that has been discussed yet? You can drop them in the chat, but if not, then I will be moving on to the planetarium section of the presentation. All right, so let me get to that. So I will have to go into this free software, which is called Stellarium. And so you can download it for free. Did I say it was free? And if you don't want to download it, there's also a version that you can use on your browser. And so you can just, have, well, less of the capabilities that you would have if you downloaded it, but it's good enough for everyday purposes. Now, this is the night sky right now. We are in Los Angeles, and so this is what we would see. Now, you might be thinking, well, where are all the stars, right? You're looking up, you're looking around. These three, those aren't stars, those are just the location of meteor showers on the software. So you look around, right, and you don't see much. And the reason for that is you live in LA, and LA has a lot of light pollution. What is light pollution? Well, there's light around the city. That light gets reflected up into the atmosphere, and then it's basically blinding us to the stars. It's kind of like if you have a flashlight and then someone has a brighter flashlight. Your flashlight doesn't really count anymore. So if you have the smaller flashlight and you're the star, that's the same effect. So we can still see some stars, right? And notice over here we have the cardinal directions. Here's north, northeast, and then if you go around, east, right? And then southeast. So these help guide people on this software. And then if you also know where your north is in real life, then you can try to see where stars can be. So um, I'm sure many of us probably have heard of Polaris, which is the North Star, and is right there. So you can barely see it, but it is there. Um, and so if I zoom in a little bit, right, now you can see it better. That's Polaris. So it is what is called a pulsating variable star. It turns out it's actually expanding and contracting. There's lots of mechanisms behind that. But it's a little ironic since it's been used as such a stable point in the sky, but the star itself is not too stable. Um, Now, if I were to lower the light pollution a little bit, just so you can see what it would look like without all these lights, here, let's go in the configuration window. Oh no, that is the wrong window. It is this window. So let's take the light pollution down to maybe 7. Let's say you're moving out a little bit in the suburbs now. Right? So now you start to see more stars. You can see Polaris a lot better. And then you keep looking around, right? And now there are a lot more stars that you can see. Still not the whole night sky. But before we go and look at the whole night sky, let's take a look around and see if we can see any of the planets in our solar system. It turns out you can. In fact, right now, Jupiter and Saturn will be in the southern direction. So if you're in LA, you'd have to find wherever the south is, and then up there you would see Jupiter. Now let me reset this to 9, which is about the light pollution in LA. You can still clearly see Jupiter, Saturn, and Venus over here. Now, why is Venus so low in the sky? Well, remember, Venus is closer to the sun than we are. So if the sun is here and Venus is here, the Earth is here, Venus has to follow the motion of the sun pretty close. So that means the sun probably set somewhere around there, right? And then Venus is kind of sinking with it, following it. Um, and so if you want to see Venus up close, all you have to do is click on this button over here and it will zoom you in. And so now you can see Venus up close. And then if I zoom in, right, that is the atmosphere. And so, oops, I just got off of it there. Now we are calibrated on Venus again. And so if you look at it, it kind of looks like when the moon, for example, when it's a quarter moon, for example. And so it turns out people have actually been able to observe these different phases of Venus um, with their telescope. So now let's pull back and let's take a look at Jupiter and Saturn. So again, if we click on this button over here in the corner, it will take you straight to that object. Now we can zoom in. Notice here we have Ganymede, and Ganymede is labeled J3. That stands for Jupiter, and then 3 is the third Galilean moon. Here we have Io, which is the first Galilean moon. It's the closest of the 4 big moons that Jupiter has. Now, what's interesting about Io is there's actually resonance between Jupiter, Io, Europa, and Ganymede. So, for example, for every 4 orbits that Io has around Jupiter, Europa makes 2 and Ganymede makes 1. What does this do? It pretty much ends up treating Io like a stress ball. So if you treat a planet like a stress ball, it's going to go very volcanic. That's why it's yellow. There's a lot of sulfur on the surface of Io because there's a lot of volcanism. It's one of the only volcanically active bodies in the solar system, the Earth being one of them. And then here is Callisto over here. So that is the moon I showed earlier with all those craters on it. Now let's zoom back out. We can go ahead and take a look at Saturn over here. And again, if we click on this, it will take you straight to it. And you can see right now, if you had a pretty decent telescope, you could actually see the rings of Saturn. What can end up happening is as Saturn moves around and the Earth moves around, sometimes those rings can either tilt towards you or they'll be edge on, and so you'll basically just see a very thin, like almost a film of a disk around it. But right now seems like a good time. And notice also we can barely see the shadow of Saturn. That's because it was recently at opposition with the sun. What is opposition? It is when you have a planet that is facing the sun directly, and we can see that from Earth. So, enough about these planets. Let's now make things a little more fun, and let's pretend that we were out in the desert and there is no light pollution. So let's take the light pollution down to 1. That is the lowest it can be. If you were out in the desert now, you could see the Milky Way. This is the disk that we see. Notice all the gas and dust in there, and it stretches all the way across the sky. And then it goes all the way around. So from northeast to southeast over, or southwest over here. Now, you might think, that is a lot of stars that we can see now, and I would agree. Let's take this one step further and remove the atmosphere, because it turns out the atmosphere is actually a big hindrance to astronomy from Earth. That's why we have some telescopes out in space. All of this air on Earth, right, the atmosphere actually obscures many stars. Now, see, this is what would happen if there was no air on Earth. A bit problematic for us, but at least you could see even more stars in the sky. Now, let's play around with some of the constellations. So right now, it is November, and so the constellations we will see here, let me label them. You have Aquarius over here, and then you have Capricorn, or Capricornus over here, Sagittarius. So the ecliptic plane goes around all of these constellations, the zodiac constellations, right? That is where you could find the ecliptic plane. That is where the sun goes around in the sky. Um, so here's Pisces and many more. Now, let's go and explore a bit around Aquarius because it turns out Neptune is hiding in there. So you cannot see Neptune with the naked eye, but if you have a telescope, that should be a decently sized telescope, um, then you might be able to see it. Earlier, I was also talking about the TRAPPIST planets, and it turns out they are in this region. They are also in the Aquarius constellation, but this software doesn't seem to have them, so I can't exactly show you where they are. Now, if we look around in the night sky, we can notice over here there is Andromeda. And so Andromeda is the biggest spiral galaxy in the local group. And so the local group of galaxies is simply all the galaxies that are close to us that form a cohesive gravitationally bound group, meaning they're not going to just fly away from each other. In fact, Andromeda is actually moving towards us, which eventually will collide in 3 billion years. So you can zoom in on it. And this, if you have binoculars and you go out to the desert, you might be able to see it. But again, right now we're viewing this and pretending there's actually no air. So if there was some air, notice it gets a little fainter. Then nearby Andromeda, so I'm going to pull back out and go down over here to the Triangulum constellation. So it just looks like a triangle. It's 3 stars. It feels a bit lazy, but that is the constellation. If you go over here, you notice another spiral galaxy, and it turns out this is the third and only other spiral galaxy in our local group. So there's about 40, 50 galaxies. All of them are irregularly shaped, so they're kind of just little clouds of stars and dust. There's only 3 spiral galaxies. Ours, Triangulum, which you can see right here, and the Andromeda galaxy. Now let's pull back out. And let's go ahead and go to the Taurus constellation. Now, Taurus will be over here. Before we do though, notice Uranus is sitting right there, so kind of tucked in between Cetus and Taurus. If you notice these stars over here, you might know them as the Pleiades, and there's actually some mythology behind the Pleiades. So they're also called the Seven Sisters, and in Greek mythology, the Seven Sisters, which all of these, so Merope, uh, Alcyone, I think, some Greek names I cannot pronounce, Electra, right? So those bright stars were the daughters of Atlas at some point. Now, Atlas was, in Greek mythology, a titan who was supposed to be holding up the world. Because he was doing that, he could not protect his daughters. And so he asked Zeus to turn them into stars to protect his daughters from Orion, which is another part of Greek mythology. He was actually a hunter in Greek mythology. Now, Atlas is also the same mythological figure that the Atlantic Ocean is named after. So there's a connection between the Earth and the stars there. Oh, one more thing about the Pleiades. If you zoom in, you might notice that there are these bright emission nebula around them. And you might also notice there are lines. And so these lines actually have to do with the magnetic field of the galaxy. And so astronomers use this to try to map the magnetic field around the entire galaxy. So what happens is the magnetic field kind of guides the dust into a certain configuration, and in this case you can see those lines stretching. Now, if we pull back out and we go to, again, in Taurus, oops, okay, so all the way down at the very bottom, this star we cannot really see yet. Um, But this star is uh, Aldebaran, which has also some mythological story, which I happen to forget. I really wish I could tell you, but I forgot the story. Now, underneath it, it seems like you have Ceres. So let's try to see if we can time travel and figure out if that is indeed Ceres. Let's just go a few minutes, and it is Ceres. So Ceres is one of those um, dwarf planets that I mentioned earlier. Now, we're about done with the current night sky. You can notice a nebula over here. Let's take a look at it. And so over here, if you take a closer look, this is the tadpoles. And so this is also another star forming regions. You can notice the little proplyds forming. And so from this cloud of gas and dust, you can see new stars forming. All right. So now let's pull back out. Oh, Spider Nebula. It was Halloween a few days ago, so you could go there for Halloween if you have a spaceship one day. Now, there's one thing I want you to notice about the night sky. Let's go back and find the north, which would be, well, it's faster this way. So, and let's go back on Polaris. Now let's focus on it, and if I were to make the night progress, you should see the night sky rotate counterclockwise around Polaris, and that is due to the Earth's rotation, which is also counterclockwise. So if you can imagine, from where you stand, there is this axis extending between you and Polaris. That is called the North Celestial Pole. And so you're basically projecting the North Pole into the sky, and it happens to meet where Polaris is. So I'll do this slowly first so you can see the effect minute by minute. Notice how the night sky is evolving. That was not a shooting star, that was a satellite. So notice it is spinning counterclockwise, and that is, again, because the Earth is spinning counterclockwise. So now that we've seen this effect, let's see what happens at midnight. What does our night sky look like at midnight? So now it is midnight of tonight. Your night sky will look like this. You have some different constellations now. You can see Gemini over here. You can see Orion over here, which in that Greek mythology story I was talking about with the Pleiades, this Orion is the Orion that Atlas was trying to protect his daughters from. So we keep going, and there are many interesting objects in the Orion constellation. So I'll begin by looking at Betelgeuse, this star over here. Now, this star is a red supergiant, and it can go off at any time. When it does, it will be a supernova, and it will outshine a lot, and I mean a lot of other objects. We will see it as a second sun when it does go out. But it is far away enough that we're completely safe. It is 500 light years away, which means the light from that star takes 500 years to reach us, and it is traveling at the speed of light, which is very fast. So we're completely safe where we are, but it would be a spectacle whenever it does happen. Maybe it's already happened. Maybe it's happened 200 years ago and we don't know yet because that light has not reached us yet. And the point I'm making here is the deeper you look in space, you're actually looking back in time because you're seeing an object at a time where the light just reached you. So the light we see from Betelgeuse right now at this moment is 500 years old. So you're looking 500 years into the past. Now, if you keep going in Orion over here, you can see a nebula. And this nebula is the Great Orion Nebula. And so that is the nebula I was showing you earlier with all the star forming regions. There's another nebula nearby. Not this one. This one over here. This nebula you might know as the Horsehead Nebula, and so this one is also in the Orion constellation. If you notice over here, there's that little feature that kind of looks like a horse head. This is a cloud of gas and dust that can form stars very easily. And then notice the reddish hues over here. Um, that has to do with the ionization of the gas. Now, if you go over here, again, another nebula. So Orion is really fun if you're just looking to find nice, pretty nebulas. There's a lot of them. This one is nicknamed Casper the Friendly Ghost Nebula. Again, another Halloween hotspot if you have a spaceship in the future and you want to go there to party for Halloween. Now, we can pull out of this constellation and go over here. Now, this is in the Gemini constellation, I think. Yes. And so over here, you see the Rosette Nebula. Now, what is special about this one is you have a star, well, four stars are in the middle, really, but one of these stars is actually ionizing all of the gas around it. And so what it does is you can see all of this reddish pink region around it. Um, and ionizing stars, they're very hot. They're also a lot brighter than our sun. And so it's just beautiful to see, but there's also um, implications about what is going on inside the nebula. So ionization means whatever elements you have, let's say hydrogen, it's losing the electron around it. So that is what ionization is. And we can now pull out of this one too. All right, so that is about it for the Sky Tour. If anyone has any questions, please feel free to let me know in the chat. If there are any particular objects that you know of and you would like to see through this Stellarium app right now, I can go ahead and show you, but I'm gonna keep these last 2 minutes for any questions that you may have. All right, so I see no questions popping in the chat. I'd like to thank you again for coming and joining us tonight. I also have the privilege to announce that the next presentation will actually be back at the Planetarium. So if you want to experience the actual dome at UCLA, the one next week, we are back in person. Make sure you are following COVID guidelines, that you have either proof of vaccination or a negative test within a day of your attendance, and make sure to bring a mask, and also questions to whoever will be presenting on at the planetarium next week. All right, so I will now end this broadcast.